This little Arduino is operating exactly as intended. It is counting from 0 through 7 over and over. What happens if I interfere with its power? It stops, obviously. How interesting. This is not a fault injection attack. If I disturb the power for a shorter period of time, such as a fraction of a second, can I make it execute the wrong instruction? Skip something? Execute different code entirely? In the last episode, we looked at why hardware security is different from software security. When you control the physical environment around a system, you can sometimes make it behave in unexpected ways. This is fault injection. And today, we are going to start with the simplest version. First, let's establish what good looks like. Up to this point, the Arduino has been counting up, 0 through 7, then repeating. Nothing complicated. As long as we don't disturb it too much, it will do exactly that. I have added a push button to the Arduino's 5-volt power rail. This push button connects the rail directly to ground, creating a low impedance short. When I press it, all of the power should flow through the push button instead of the Arduino. Let's try it. And that's it. We stopped the processor. More importantly, there is something we can learn from this. I didn't hack anything, but nor did I cause some unexpected behavior. When I interrupted the power, the board shut itself down. When power came back, it must restart from the beginning. So, when I release the button, the Arduino boots back up again and starts the program from the top. This can be our new baseline. The Arduino operates at a steady 5 volts. What if I don't completely remove the power or short it out? Instead, what if I caused a very brief voltage disturbance on the supply? The processor might continue executing, but something could have happened during that disturbance, and there we have a voltage fault injection. Normally, researchers don't shut down the processor like we just did. They want a carefully controlled voltage disturbance at a carefully selected point in time. One of the papers we're using for this series describes voltage fault injection as manipulating the processor's supply voltage to create timing violations inside the chip. Further, the processor is synchronized to a clock, and its internal operations have very tight timing requirements. If we disturb the electrical conditions, we can violate those timing requirements. Thus, fault injection is about both voltage and timing. Research shows that changing the processor's clock frequency can change its susceptibility to both voltage and EM fault injection. The clock isn't just telling the processor when to work, it can also affect how vulnerable it is to a physical disturbance. Okay, that's great. So, what if we get that timing right? The processor could experience an exception, instructions can execute incorrectly or not at all, or registers can become corrupted. Or nothing could happen. Of course, we could always go the electromagnetic route. Researchers generated strong EM pulses near the processor, allowing the disturbances to couple into the chip. They then mapped where these faults can occur. They discovered that EM pulses at different regions can cause different effects, from crashing the processor, corrupting internal memory, or generating exceptions. Thus, understanding fault injection is really also about understanding the physical behavior of the processor itself. Back to our victim. Right now, all we have demonstrated is that shorting the board stops the processor. This is not really sophisticated, but it shows us the exact fault relation we are looking for. Power, processor, failure. If I tried to short the Arduino manually for a very short time, unfortunately we have the same effects. This is because my finger is not nearly fast enough for what we're trying to do. If we actually want to perform fault injection, we need some electronics that can switch the power much faster. So, our next step is to replace the buttons with actual electronic switching. This will allow us to play with voltage glitches and get the timing right. And eventually, we will try to get the Arduino to perform something we didn't program it to do. See you next time.